transferred the bromine, and we've got the organic product. We started with a radical. We had a molecule. We got a molecule. We have to end up with a radical. So that's that first. We start with a radical, neutral molecule. We end up with a molecule. We have to end up with another radical. And what does this radical now do? The only molecule that seems to be around at this stage, which has relatively weak bonds, is some more hydrocarbon starting material. And now it will again transfer the hydrogen. And the result of that is succinimide, the bromine succinimide plus the allyl radical again. And this one now can, sorry, I'm going to put it up a little bit so it's easier to see from the back. This radical now can re-enter this loop up there and continue doing it until all the reagents have been used up. And the combination of these two reactions, 1 and 2, 1 plus 2, is a radical chain reaction. If you add 1 plus 2, if we added these two up, we would cancel out the radicals on this side, we would cancel out the radicals on that side, and the overall addition is that we start off with propene plus NBS, and I'm going to draw it just in letters. Gives the bromide plus succinimide. And the catalyst for that reaction, the catalyst, if you remember way back, the catalyst was the peroxy radical or the peroxide. Okay? So that's a general kind of reaction, and in a sense just to try to sort of finish, to try to at least get to the point of the polymerization reactions that I'm going to do. I think I can sort of readily at least do the type of polymerization that you do in the lab. The concept of the polymerization. And one of the polymerizations that's making all kinds, it's done on multi-million ton scale, is the production of polystyrene. For your coffee cups from Tim Hortons or wherever you, or Coca-Cola at McDonald's, whatever you want, you participate in. The polymerization reaction is drawn in the following way. You start off with a molecule, styrene, that's the common name, or vinyl benzene is another common name. And it's basically a CH2 group with a phenyl ring on it. There are no allylic carbons here, by the way. So, and all you do is you heat this in the presence of a peroxide, and very often you use benzoyl peroxide. Okay? And you heat this to about 80 degrees. And you get polystyrene, which we end up drawing as simply CH2 phenyl, taken many, many times, like a chain, taken many, many times. And the way I did it today, the two of them together, you should see that there is a difference. It's the absence of those allylic hydrogens which makes this chain, this reaction give a polymer, and the other one simply a substitution product. But it's the same kind of idea. So, again, first thing, use the catalyst. There's a weak bond here. And when we heat that, it breaks into two, and we get two of these. So these two. So we have an alkoxy radical. Now this compound, this radical, has a special property that it would really love to expel CO2. And it can expel CO2 by taking one electron from this bond, pairing it up, and getting a phenyl, and ending up with a phenyl radical. Sorry, it's going to be green plus CO2. So, what's a phenyl radical? It's just a benzene ring with one of the hydrogen is missing. All those, there are hydrogens there, and there. And this molecule wants to desperately, or this species desperately wants to pair up an electron. The only thing that's in the system is this molecule. There's nothing else there. These bonds are pretty bloody strong. So where else can it get an electron? If it can't do a hydrogen transfer, where else can it get one electron and make a bond? Somebody, come on. You can take, the double bond is always available as either a source of one or two electrons. So you can take one electron from there and one from there, and it will then, to make it easier to draw, make a new bond here, a CH2, and a C, and an H, and a phenyl, and a radical. Now I chose that direction because that's a radical next to a phenyl group, next to a sp2 carbon, and this is a delocalized